Hi, class. I'm taking the time today to go through some of the answers that were poorly done or that some people need just some assistance with, because this is important to understand the rest of this chapter. Okay, so I went through in the last video how to answer this question and through some of the answers as well. So just to fill in what's left. So for water, water can be an acid or a base for both Bronston-Lowry and for Arrhenius. This is going to be an acid for both Arrhenius and Bronston-Lowry. That's phosphoric acid. This is going to be a base for both of them, calcium hydroxide, acid, acid. And then this one here, this one is going to be a proton donor, so it's going to be an acid for both of them as well. This one here, there's a hydrogen there, acid, acid. And then this one here is the tricky one, okay? So this can be both acid or base. And it's because it is, if you're looking at H2PO4 with water, it can either go one way and can be a proton acceptor and go back to phosphoric acid, or it can be a proton donor and become a 2- species and then produce hydronium ion. Okay? So that's just going through there. It takes some time recognizing acids and bases and if they're Bronston-Lowry or Arrhenius. The other thing that I want you guys just to make sure, so you're looking at strong and weak acids. Does it say on here? Okay, I'm just going to write it. You need to know the 6 strong acids. Okay, and so that's hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, phosphoric acid, and then I'm forgetting one. Oh gosh, which one is it? I want to say hydrobromic acid. I'll find out which one, the last one is, okay? But mostly we're dealing with hydrochloric acid, sulfuric acid, and sometimes you'll see the other ones, but mostly you're going to see these ones. Let me just look up the last one. So 6 strong acids. And then what does it mean to be a strong acid? It means that the dissociation is going to be pretty, okay, I was right. Hydrobromic and hydroiodic. So the ones with the halogens, okay? And sorry, this one is HClO4. So all these ones, it means that the dissociation is basically 100%, that there isn't going to be any of these entities left together after it's placed in water. So it's pretty much 100% dissociation. Okay, so I wanted to go through question number 5 and question number 6 with you guys because on page 386, because this was not well done and it was using fundamentals from grade 11. So I was making the assumption that you guys could remember that stuff. And because you guys weren't able to, let's go through the answers. So we're looking at 5A, 4.5 mole per liter of hydrochloric acid. Well, the concentration of hydrogen, because it's a strong acid, is going to be 4.5 mole per liter. Okay, that one's pretty easy. B, 30 milliliters of 4.5 mole per liter hydrobromic acid, another strong acid, diluted to 100 milliliters. So this one is going to involve using C1V1 equals C2V2. It's not additive, okay, because you're diluting, so let's put in the numbers. The first concentration is 4.5 moles per liter, and it's 30 milliliters. You're trying to find concentration 2, and you diluted it to 100 milliliters. Okay, so it's not additive. You just are filling up the beaker or whatever vessel to the 100 milliliter mark. So you should get a concentration. Once you do this, it's going to drop from 4.5 to 1.35 molar. Okay, letter C, this is where you're going to have to look at, okay, so here's the perchloric acid plus sodium hydroxide. This is a neutralization, okay? So yeah, you're going to have sodium perchlorate and water being formed, but it's a 1-to-1 ratio. Okay, so my students last year, you probably didn't see me do this table method. You might not have seen this before, but this is what I've kind of changed to because I like this better. So I just fill in the concentration of all my entities. And then, so let's see, I have 18.6 milliliters. You know what, you guys have already read these questions, I hope. So I'm just going to fill in all the information that I was given. And then, yeah, you were given all this. Okay, so when you calculate the number of moles, you're going to see, let's see. Oh yeah, you guys get to see what my email looks like. You can see all the notifications. Okay, you're going to see that this is the excess reactant. And so we are going to be left with hydrogen left over. How much hydrogen? Well, we're going to subtract the number of moles from both of them. And because you're mixing the two solutions together, you're going to get a very much more dilute concentration of hydrogen, which makes sense because some of the hydrogens are going to react with the hydroxides and form water. And then they're taken out of, they're no longer hydrogen or hydroxide. Okay. And my house is very noisy. I hope you guys can't hear that too much. Okay, for this one, we're combining nitric acid plus calcium hydroxide. And look, now we're going to need 2 nitric acids to produce calcium nitrate. And you're forming 2 waters. It really doesn't matter what you're forming over here, okay? But from this, we're going to see that we need twice as much nitric acid to neutralize the calcium hydroxide. So when I'm placing my numbers in here, okay, so I'm going to just, oops, I'll do it in blue so that it looks different. All these numbers I'm getting straight from the question. Okay, and then I'm going to find out how many moles that I have. Well, here I have 3.1325 times 10 to the minus 3 moles of nitric acid. And here I have 5.664 times 10 to the minus 4 moles of calcium hydroxide. The problem with this is that you need twice as many of the nitric acid as you do the calcium hydroxide. So I put this extra step where I'm going to divide my number by 2. I'm going to get 1.57 times 10 to the minus 3. And I still have 5.664 times 10 to the minus 4 over here. This is still going to be my excess reactant. I'm going to do exactly the same thing over here, where I'm going to calculate the concentration of hydrogen. Okay, but the thing is that whatever number I have here, 1.57 times 10 to the minus 3 minus 5.664 times 10 to the minus 4, I have to multiply this by 2 because this is the excess amount of nitric acid, but we've already divided that number over here by 2. So then I'm going to have to multiply it again by 2 to find out the number of moles. If this is too confusing, you can do it the long way. I'm just taking the shortcut here. And then you just add the 2 volumes together. That doesn't change. And so then I get, okay, so this is the number. If you got 1.88 times 10 to the minus 2 mole, you forgot to multiply it by 2. Okay. So then the correct answer is 3.76 times 10 to the minus 2 molar. Now, question number 6 is the exact same thing, but with bases. So if I marked like 6 completely wrong on your homework that you handed in, go and try them. The answers are in the textbook. So because I also have to reiterate, because the answers are in the textbook, I am marking your process work. Okay. Don't just write down the answers. I really don't care about that. I care about your process work. Now, some of you guys did have issues with going from pH, POH, things like that. So how about this? Let's take this value over here and let's pick, I don't know, let's pick the Starry Night one. So my concentration of hydrogen, which really is hydronium, is going to be 3.76 times 10 to the minus 2 molar. Let's calculate the pH, the POH, and then the concentration of hydroxide. Okay, I want you guys to be able to do that. So the formula for pH is minus log of the concentration. So let's do that on our calculators. Minus log 3.76 times 10 to the minus 2. Then I get 1.42. Okay. The POH. Now, you guys know that the scale of pH goes from 0 to 14 with 7 in the middle. This is the realm of acids. This is the realm of bases. Well, guess what? Our formula is 14 equals pH plus POH. They're reflective, okay? They are complementary. So if I want to calculate the POH, it's 14 minus pH, 14 minus 1.42. Oh, something's making a noise. And I get 12.58. Okay. And so when I'm calculating my concentration of hydroxide, it's going to be 10 to the power of negative POH. It's the same with concentration. If I had just the pH, I would do 10 to the power of negative pH. So here I'm going to put 10 to the power of negative 12.58. Let's find out what that is. 10 to the power of negative 12.58, 2.63 times 10 to the negative 13. 2.63 times 10 to the negative 13 mole per liter. Is there another way to do it? Yes, there is. So we know this. Okay. We have that the equilibrium equations, but we also know that when you multiply the two concentrations of acids and bases together, they're going to equal 10 to the minus 14. So concentration of hydrogen and concentration of hydroxide. So let's see, what's my original concentration of hydrogen, 3.76 times 10 to the negative 2. 3.76 times 10 to the minus 2 times hydroxide. I hope you guys can't hear that because people are swearing outside, but oh well. Okay, let's try this together. 10 to the power of negative 14 divided by 3.76 times 10 to the negative 2 equals, okay, so we're a little bit off, but within the same realm. So times 10 to the negative 2? Yeah, okay, so 2.66 times 10 to the minus 12 mole per liter. Okay, sorry, minus 13. Okay, let's leave it at that for this. Please try your, so when you're putting this in your calculator, put 1 times 10 to the minus 14 as well. Okay, and so then you get times 10 to the minus 13 here. Try this. Let me know if there's any other questions that you want me to go through for the homework, and take care.